In this video, we're going to go through a first quarter pre-calculus exam review. There's timestamps in the description below if you want to hop to a particular part of this video. But let's jump into this video and we'll go through the problems together here. So number one says, determine the quadrant or quadrants where the coordinate xy is located such that x divided by y is less than 0. Okay, so what they're testing us on here is that we're familiar with our four quadrants. In the first quadrant, the x is positive and the y is positive. In the second quadrant, the x is negative and the y is positive. In the third quadrant, both the x and the y are negative. And in the fourth quadrant, the x is positive and the y is negative. But notice when you divide the x and y, in order to get a number less than 0, meaning negative, one of the values has to be positive, one of the values has to be negative. So that's only going to occur here in the second and fourth quadrant. I'll just write that using Roman numerals 2 and 4. Okay, so definitely something to memorize there. Number two, it says find the distance and the midpoint between 2, -3 and -3, 9. Now you might want to pause the video, some of these problems, see if you can do them on your own and kind of check them with me as we go through this. But important formulas you might want to add to your study sheet or your formula sheet would be the distance formula, x2 minus x1 squared plus y2 minus y1 squared. And then you add them together and take the square root. So if we do the distance, you can see that this is like point 1, x1, y1. This is point 2, we call that x2, y2. So we're going to subtract the x coordinates. We've got -3 minus 2 squared. And we're going to subtract the y coordinates. So that's going to be 9 minus -3 squared. Add those together and take the square root. So -3 minus 2 is -5. -5 squared is 25. 9 minus -3 is like 9 plus 3, that's 12. 12 squared is 144. If we add those together, we get the square root of 169, which is equal to 13. So that's the distance between these 2 points. Now for the midpoint, another formula you want to memorize or add to your study sheet here, your formula sheet, is x1 plus x2 divided by 2 and y1 plus y2 divided by 2. Like that. So what you're doing is it's like an average. You're adding the x's together and dividing by 2, and then you're adding the y's together and dividing by 2, and that'll give you the point in the middle. So for this one, what we're going to do is we're going to say 2 plus -3 divided by 2, and we've got -3 plus 9 divided by 2. Now all we have to do is simplify. This is going to give us -1/2, and this is going to give us 6 divided by 2, which is 3. So you can see our midpoint is at -1/2, 3. Okay, so for number 3 now, it says find the x and y intercepts of the graph. So intercepts just means where does it cross that x-axis or the y-axis, right? So what you can do, if you remember this from earlier in math, is you can make a little table like this. Just set x to 0 to find the y-intercept, set y to 0 to find the x-intercept. So you're setting the opposite variable equal to 0. So if we put 0 in for x here, you can see that's going to be 3 times 0, which is 0, plus 1 is 1. The square root of 1 is 1. Right? So you can see that the y-intercept here is going to be at 0, 1. Now for the y-intercept, I'm sorry, I said that wrong. For the x-intercept, we're going to set y to 0, right? So if we put 0 in for y, we just have to solve for x now. So if we square both sides of this equation, 0 squared is still 0. If we subtract 1 from both sides, you can see we've got 3x equals -1. Divide both sides by 3, and you can see that our x-intercept is -1/3, 0. So this just kind of helps you when you're graphing. 0, 1 would be right here, and -1/3, 0 would be like right about here. And so now you have an idea about what the graph is going to look like, okay, or at least a couple key points. Okay, so for number 4, see if you can try this one. It says write the standard form of the equation of a circle with the center at 0, -2, and the diameter of 6. Okay, so another important formula you want to add to your formula sheet here is the standard form of the equation of a circle. So it's x minus h squared plus y minus k squared equals the radius squared. So h and k, that represents the center point. R represents the radius, but then you're going to square it. Okay, so this comes from the distance formula. But let's see if we can substitute these values in. So we've got x minus 0 squared plus y minus -2 squared. Now the diameter is 6, which means that the radius is equal to 3. So 3 squared is 9. Now I can simplify this a little bit more. X minus 0 is just x, so we could say x squared. Here when you subtract a negative, it's like adding the opposite, so that's y plus 2 squared equals 9. So that's your standard form of your equation of your circle. Okay, for number 5 now, see if you can do this one. It says if negative 3, 4 is on a graph, name another point that must be on the graph if the graph has origin symmetry. Okay, so what does that mean, origin symmetry? Well, for example, let's look at a graph that has origin symmetry. Say, for example, like y equals x cubed. See, if you take a point here and you rotate it 180 degrees about the origin, it would match up with a corresponding point right there. So our test for origin symmetry is like this, x, y. Okay, so basically you can find the corresponding point by multiplying the x and y values by -1. And what that does is that rotates that figure about the origin. So in this case, negative 3, 4, a corresponding point would be positive 3, negative 4. And you got it. Okay, number 6, it says the graph y equals 2x cubed minus x has symmetry with respect to the x-axis, y-axis, or origin. Okay, so here's the test that you want to memorize. When you're testing to see if it's a reflection, okay, over the x-axis, meaning it has symmetry with the x-axis, what you want to do is you want to replace x and y with x comma negative y. So this is x-axis symmetry. And if you want to test for y-axis symmetry, what you do is replace the x in the equation with negative x and the y with positive y. So that's y-axis symmetry. And then if you're testing for origin symmetry, you replace both x with negative x and y with negative y. And what happens is when you replace those, you do those substitutions and you simplify, if you get the original equation back, that tells you that it has symmetry with regard to that x-axis, y-axis, or origin. So I'll show you what I mean. So in this first one, see x and negative y. If we replace y with negative y and x just with x, when we look at that equation, see, even if I multiply everything by -1, y equals negative 2x cubed plus x, see how I'm not getting back the original equation? That tells us that it's not symmetric with regard to the x-axis. Now let's test the other one. Let's say we replace x with negative x and y with positive y. So here we get y equals 2 times negative x cubed minus negative x. But when we simplify, a negative to an odd power is a negative, so that gives us negative 2x cubed, and a negative times a negative is a positive. But you can see we're not getting back that original equation, so that tells us it's not symmetric about the y-axis. Now for the origin, we're replacing both the x and the y, okay, with negative x and negative y. And when we simplify here, let's see what happens. We have negative y equals negative 2x cubed plus x. If I multiply everything by -1 to get this to be a positive y, the signs are going to flip. And when we look at that, we see, oh, it's the same as the original equation. So this tells us that it has rotation about the origin. So you might want to add these to your note sheet for testing the different types of symmetry. Okay, let's go to number 7. It says, find equation of the line that passes through these 2 points. Okay, so you remember how to find equations of lines. First thing we have to do is we have to find the slope. And remember, the slope is y2 minus y1 over x2 minus x1. So I'm going to say 4 minus 5, which is -1, and -1 minus 2, which is -3. The two negatives cancel, so you can see our slope is 1/3. Now, you probably also remember the point-slope form of the equation of a line. So x1, y1 is the point that the line goes through, and m is our slope. So in this case, I'm just going to put 1/3 in for m. I'm just going to use this point over here, 2, 5. So y minus the y coordinate equals x minus the x coordinate. And then if you want, what you can do is you can distribute the 1/3. So this is 1/3 x minus 2/3. And then what I'm going to do is I'm going to add the 5 over here. Okay, now I'm just going to get common denominators. This is 15/3 minus 2/3, which gives us 13/3. Okay. And that's our equation of our line in slope-intercept form. But you could probably leave it in the point-slope form. That would be fine too. Okay, for number 8 now, it says find the equation of the line that's perpendicular to this line and passes through this point. So when we talk about lines that are parallel, remember those have the same slope. When we talk about lines that are perpendicular, they have opposite reciprocal slopes. So in this case, we have to figure out what the slope of this line is. And what I'm going to do is I'm going to rearrange it by subtracting 3x from both sides of the equation. If I divide everything by -5, now we have it in slope-intercept form. So we can see the slope is 3/5. The perpendicular slope is going to be -5/3. We know it's passing through this point, so I'm going to do y minus -2 equals -5/3 x minus 3. And now you can see it's in the point-slope form. But let me simplify this a little bit more. Distribute, that's going to give us negative 5/3 x plus 5. And this is y plus 2. And if we subtract 2 from both sides, we get negative 5/3 x plus 3. And now it's in the slope-intercept form. Okay, let's try number 9. So it says, given that f of x equals 2x squared minus x, how would you find f of x plus 2? So here they're testing us on function notation, how to work with functions. But remember, whatever's in the parentheses, that goes in for x on the right side of the equation, right? But in this case, this is like our new input, our new x value. So what we're going to do is we're going to replace x with x plus 2. So we get 2. Instead of x, I'm going to put x plus 2. Instead of x here, I'm going to put x plus 2. And now we just have to simplify. So x plus 2 squared really represents x plus 2 times x plus 2. Okay, here I'm just going to distribute the negative, so that's going to be negative x minus 2. Here you can FOIL this out. You're just going to get x squared plus 4x plus 4, all multiplied by 2. Okay, so this gives us 2x squared plus 8x plus 8 minus x minus 2. Combine like terms, 8x minus 1x is 7x, and 8 minus 2 is 6, and that's your final result. So again, it's just a substitution. For number 10 now, it says, given f of x equals this piecewise function, how would you find f of negative 3? So notice that with piecewise functions, you're on this graph when x is less than or equal to negative 2. You're on this graph, y equals 5, when you're in between negative 2 and 3. And then you're on this graph when x is greater than 3. But when we look at negative 3 here, see how negative 3 is less than or equal to negative 2? That means we're going to be on this part of the graph, that part of the piecewise graph. So all we have to do now is replace x with what x equals, which is negative 3. So that's 3 times negative 3 minus 1. So that's negative 9 minus 1, which is negative 10. Okay, so it's just basically trying to figure out, where does that x value fall on which graph. So for number 11, it says, given f of x equals this equation, how would you find the zeros? So what does that mean when they say find the zeros? Well, zeros means that the y value, f of x is like our output or our y value, is 0. So all I'm going to do is I'm going to set this whole equation equal to 0, and then we're going to solve. Now there's a couple different ways to do this. You could use the quadratic formula, you could factor, you could complete the square, etc. But for this one, what I'm going to do is I'm just going to factor, okay, and you can see that this is going to be positive 8 and negative 1. See, 8x and negative 5x gives you 3x. 8 times negative 1 is negative 8. 5x times 1x is 5x squared. If you need help with factoring, check out some of my factoring videos on my Mario's Math Tutoring YouTube channel, and I can go over that with you to show you how to factor trinomials. But now all you have to do is set each group equal to 0. So what I'm going to say is 0 equals 5x plus 8, and 0 equals x minus 1. So if we subtract 8 from both sides, divide by 5, you can see that x equals negative 8/5. And if we add 1 to both sides here, you can see that x equals 1. So our zeros are going to be 1 and negative 8/5. And again, what the zeros mean, it's where y equals 0. It's where it crosses the x-axis. These are the x-intercepts. Okay, so for number 12 now, we're talking about the domain. So what is the domain? Well, the domain is whatever you can put into the equation in place of x, right? The range is what comes out. Those are the y values. But for the domain, you want to be careful because you can't necessarily put anything into this equation. For example, we don't want this to be negative because when you take the square root of a negative, you're going to get imaginary numbers. So what we're going to do is when you have square roots or fourth roots or even roots, take whatever's underneath the radical and make it greater than or equal to 0. So if I solve this by subtracting 4, we get negative 3x is greater than or equal to negative 4. Divide both sides by negative 3. But remember, when you divide or multiply an inequality by a negative, what happens? The inequality sign changes direction, right? So now x is less than or equal to 4/3. Sometimes it's helpful to graph this on the number line. So it's 4/3 or less. So when we write this in interval notation, you could write it in inequality notation, but interval notation would be like this: negative infinity to 4/3, including 4/3, right? Because it includes that point, but it doesn't include negative infinity. You can't reach negative infinity. You want to go from left to right. Okay, but for part B though, now we have a fraction. With fractions, you don't want to divide by 0. That's undefined. So when you have a fraction, make sure that the denominator is not equal to 0. We're going to temporarily set it equal to 0 to find out what x would make the equation, the denominator 0, right? So I'm going to add 1 to both sides. So 3x equals 1. I'm going to divide by 3, so x equals 1/3, but really we don't want x to be 1/3 because we don't want the denominator to be equal to 0, right? So again, if we go to the number line, here's 1/3. It could be all of these values, can't be 1/3, and it could be all those values. So the domain is what x can be, so it's everything but 1/3. Now if we write this in interval notation, you can see it's negative infinity to 1/3, not including 1/3, that's why I'm writing the parentheses, union 1/3 to positive infinity. So you want to think about going from low to high or left to right. Okay, question number 13, it says, given f of x equals 3x squared minus 2x, find the difference quotient. And remember, the difference quotient is f of x plus h minus f of x all over h. Don't get this confused with the derivative, which you'll be learning a little bit later in pre-calculus and into calculus, where you're finding the limit as h approaches 0. Here we're just finding the difference quotient. So the way you work with these ones is, again, it's just like what we talked about earlier about working with functions. Whatever's in the parentheses, that goes in for x on the right. Now if there's more than one x, you would replace both x's with that x plus h. So just think of it as a substitution. So what we have is 3 times x plus h squared minus 2 times x plus h. Okay, now minus f of x. Now when you think of f of x, that's this entire function. But where some students make a mistake is they forget to put it in parentheses, because you're really subtracting right here f of x, this whole original equation, okay? And then it's all divided by h. So now we just have to do a lot of arithmetic. You want to be a little bit careful here. So when you FOIL out x plus h squared, remember this is x plus h times x plus h. So that's going to come out to x squared plus 2xh plus h squared. If you need to, just write this x plus h, do the distributive property twice, or FOIL. Here we're going to distribute the -2, so this gives us -2x minus 2h. And then here we're going to distribute the negative, that's going to give us -3x squared plus 2x, all divided by h. Now, let me see if I can distribute the 3 here. So this gives us 3x squared plus 6xh plus 3h squared minus 2x minus 2h minus 3x squared plus 2x. So you can see it's quite tedious. You have to be careful you don't make little mistakes, arithmetic mistakes. But now we're going to combine like terms. Now, notice the 3x squared and the -3x squared cancel. The 2x and the -2x cancel. So we're just left with 6xh plus 3h squared minus 2h, all divided by h. Notice there's an h in each one of these terms in the numerator. So what I'm going to do is I'm going to factor out that h. So 6x plus 3h minus 2, all divided by h. We can cancel the h's out, and our difference quotient is just going to be 6x plus 3h minus 2, and you got it. Okay, let's look at number 14 here. It says state whether the function is increasing, decreasing, or constant. Now remember, it's just like reading from left to right. If the graph is going up to the right, that's like a positive slope, that's like increasing, right? If it's going down to the right, that's decreasing. If it's horizontal, that's constant. So I kind of scan from left to right and I look at where's the graph going up to the right. Well, it looks like here and here. So what we're interested in is not the y values. Some students make the mistake of looking at the y values. We're interested in for what x values are the y values increasing. So as I go from left to right, see I'm going up, 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 up. So that's when x is what? So I'm just going to write increasing from negative infinity to 1 to -3, okay? Union, okay, from when x is 1 and onward. So that's from 1 to positive infinity. Now, the important thing you want to notice here is see how I use these parentheses, so like an open interval. And the reason is because when you get to -3, that's where it's changing from increasing to decreasing. So you don't want to actually include -3. Same thing over here, even though this is a closed point here, when you get to 1, it's changing from constant to increasing. So with increasing, decreasing, constant, you're always going to want to use open intervals. When you're talking about domain and range, that's different, and we'll talk about that in number 17. Okay, so I just did increasing. For decreasing, you can see it's going down to the right here, and you can see that's when from x is from -3 all the way to x equals -1. So we're going to say -3 to -1, and then constant, I'll just draw like a horizontal line to abbreviate there, is when x is from -1 to +1, and you got it. Okay, let's look at number 15. It says find the relative maximum. Okay, so for the same graph. So remember when we talk about relative maximum, relative minimum, these are basically where the graph is bending or turning. And relative to the points that are on either side, it's the highest. Now you can see it's not the absolute maximum. This graph keeps going up, but where it's bending here, it's relative to the points that are on the other side. This is a high point. So at -3, 2, that is our relative maximum. For part B, it says find f of 2. So what's f of 2 mean? Well, remember, whatever's in the parentheses, that's like our x coordinate. So when x is equal to 2, f of x is really saying what's the y value? Well, you can see the y value at when x equals 2 is actually 0. And you got it. So let's look at number 16 now. It says determine whether the function is even, odd, or neither. Okay, so here's something you might want to add to your note sheet. When you replace negative x, when you replace x with negative x in your function, if you get back the original function f of x, that tells you that the function is even. Now, what does that mean, even? Well, even means it's going to be reflection over the y-axis. So you could think of this as y-axis symmetry, but when we test it in this fashion, we call it even. Now, if you replace wherever you see x with negative x, and you get negative f of x, meaning like you have the original function, but it's multiplied by -1, then we call this an odd function. Okay, an odd function means it's a rotation about the origin. So what we're going to do is we're going to take this function here, and we're going to replace x with negative x. So let's do that. So negative x, so I'm going to put in negative x square root 2 times negative x squared minus 1. So I'm just doing a substitution. Wherever I see x, I'm replacing it with negative x. Negative x squared is just going to give us positive x squared, and we have negative x. So when we look at this function here, what you can see is, you see this right here? It's just like our original function. The only difference is it's multiplied by -1, so that tells us that this is an odd function, and then when we go to graph it, we'll see that it's a rotation 180 degrees about the origin. Okay, for number 17 now, we're looking at the domain and the range. So now remember, domain means what can the x values be, and the range means what can the y values be. My technique that I use when I do this is when I'm looking at what the domain is, I scan from left to right, okay, along the x direction with a vertical line, or like my marker here. So when I scan across, see how there's not any points over here at -5, -4, -3, it's open, but from -3 to 0, see how there's points on the graph, it's crossing there? So what I would say for the domain is it doesn't include -3, but it goes all the way up to 0, including 0, union. Now see how there's a little bit of a gap here between 0 and 2, and then it picks up at 2 and greater. So we're going to say from 2 to positive infinity, but you can never reach infinity, that's always going to be open. Now when I do the range, I take a horizontal line like this marker, and I scan from low to high, right? So you can see this keeps going down, down, down. So I'm going from negative infinity up to 0, okay? And this is open, this is closed. So you can see it continues to cross the graph here, right? And then even when you go up here, it's crossing at half, 1, 1.5, 2, and then up here there's not any points at this height, at this y value. So you can see the range is negative infinity all the way to 2, including 2, but not above. So that's what I do, scan left to right for domain, low to high for range. Okay, number 18, it says find the average rate of change from x equals 2 to x equals 5 for this function right here. Now when they say average rate of change, what they're really telling us is they want us to find the slope. So the first thing we need to do is find the y coordinates of these 2 points so that we can then find the slope between the 2 points. So what we're going to do is we're going to put 2 into our function in place of x, so we get 3 times 2 squared plus 2 plus 1, which let's see equals 4 times 3 is 12, plus 2 is 14, plus 1 is 15. Okay, so we have the point 2 comma 15. And then if we put 5 in, we get 3 times 5 squared plus 5 plus 1. So that comes out to 25 times 3 is 75, 80, 81. So now we have the point 5 comma 81, and now we just have to find the slope. And remember, the slope is the difference in the y's over the difference in the x's. So we have 81 minus 15 over 5 minus 2. And so this comes out to, let's see, 81 minus 15. What is that? 7, 11, 6. Yeah, so 66 divided by 3, which is a rate of change or a slope of 22. Okay, so for number 19, it says evaluate the greatest integer function at negative 4.1, and then at 2.99. Now, if you see these interesting looking brackets here, that tells us greatest integer function, or sometimes they'll draw it like this with the little bars on the bottom, which really tells us to round down basically to the left on the number line. So what I like to do sometimes with these problems is plot them on the number line. Here's negative 4, here's negative 5, and here's negative 3. Negative 4.1 is right about there, but we have to round to the left, meaning round down. So this is actually negative 5. Some students mistakenly will say, oh, 4.1, I'm just going to round down to 4. But you have to think about the number line you're rounding to the left, the next integer to the left. Now if this is negative 4, then it would just stay at that integer value, negative 4. But if it's in between integer values, you're going to have to round down to the next lowest integer. So for 2.99, let's see, here's 2, here's 3. 2.99, it's almost to 3, but not quite. We have to round down to the next integer, which is going to give us 2. Okay, so for number 20, we're also working with the greatest integer function. See those brackets again. But what we want to do now is we want to graph this function using transformations. So the key here is to really be comfortable with, how do you shift the graph, how do you stretch the graph, compress the graph, reflect the graph. But you can see here, if we were to just take a look at our basic greatest integer function, which is like this, let's make a table of values. I'll show you how this works really quick. So say if you had like 0, that would still be 0. 0.5, that would be 0. 0.999, that's going to be 0. And then as soon as you get to 1, you're at 1. 1.5 would round down to 1. 1.9 would round down to 1. And 2 would be 2. So if we were to plot these points, what this greatest integer function looks like is like this. So you're going to be at 0, 0. 0.5, you're at 0. 0.99, you're at 0. As soon as you get to 1, you jump up to the next integer value, which is 1. Okay, and so then here 1.5 you're at 1, 1.99 you're at 1. As soon as you get to 2, you jump up to the next integer value. So what they call this is a greatest integer function, but oftentimes referred to as a step function because it looks like stairs going up like that, right? And once you get a few of the steps, you can repeat that process like I'm doing now. But what we're doing here is, you can see what the 2 does is going to be stretching the graph. It's going to be multiplying the y values by 2. So these stairs, instead of going up 1, 2, 3 like that, they're going to be going from 0 to 2 to 4 to 6. So it's doubling the y values. And this is going to be shifting the graph right 1. See the minus 1, the one group with the x has the opposite effect. So minus 1 is going to the right one. If it was plus 1, it would go to the left one. And this value here, the 2, is going to shift the graph up 2. So what I'm going to do now is let's do this in steps. So I'll see if I can show you how this works. So the first thing I would do is graph these steps. But what I'm going to do is I'm going to do the stretch first. So these are going up by 2 each time. Okay, like that. Okay, so that's a vertical stretch. And then what we're going to do is we're going to take each of these steps, we're going to move them right 1 and up 2. So this one right here is going to go right 1. Okay, up 2. So that actually coincides. I don't know if you can see this. You're going right 1, up 2. Same thing here. This is going right 1, up 2. So this graph is actually not looking any different than it does right now. But if you were to describe the transformations, that's how you would do it. You'd say shifting right 1, vertical stretch by 2, and then shift up 2. Okay, so for number 21, it says write the equation for the parent function f of x equals square root of x when you reflect it over the y-axis, okay, and then you shift up 2. So what would be the new equation here? Well, let's call the new equation g of x, okay? And what's happening is when you reflect over the y-axis like this, what happens is the x-coordinates are going to have the opposite sign. So it's going to be multiplied by -1, so negative x. And then when you shift up 2, this is going to be plus 2. Now notice it's not grouped with the x. When it's grouped with the x, that's when it's going to affect the x direction, the horizontal direction. When it's not, like out here, it's going to affect the vertical shift up and down. If it was -2, it'd go down 2. Okay, for number 22 now, we're working with composition of functions. We've got f of x equals 2x minus 3 and g of x equals x squared plus 1. It asks us, what is f of g of 2? Okay, so what you want to do is you want to work from the inside out. So we're going to start by the inside, the g function, and it says put 2 into the function on the right in place of x. So 2 squared is 4, plus 1 is 5, so this comes out to 5. Now we're finding out what's f of 5. So again, whatever's in the parentheses goes in for x on the right. That's 2 times 5 is 10, minus 3, which is equal to 7, and you got it. So kind of like a two-step process. For letter B, though, what we have is g of f of x. See this little symbol here? This really represents like g of f of x. So another way to write it. But what we're doing is we're putting the f function into the g function. So in this case, our f function is 2x minus 3. And what we're going to do is we're going to now take whatever's in the parentheses. Remember how that goes in for x on the right side? We're going to put 2x minus 3, that quantity, in place of x and square it and add 1. So this is going to be 2x minus 3 squared plus 1. Now if you want to FOIL this out, it comes out to 4x squared minus 12x plus 9 plus 1 more, which is plus 10. But you could leave it like that or like that, either way. Okay, number 23, it says find the inverse of f of x equals x plus 4 all divided by x minus 3. So remember, when you find the inverse, what you want to do is you want to interchange the x and y and solve for the new y. So when you think of f of x, you could think of this as the y value. So what I'm going to do is I'm going to interchange the x and y. So we have x equals y plus 4 over y minus 3. And then what we can do is we can think of x as x divided by 1. Anything divided by 1 is itself. And we can cross multiply to get rid of the fractions here. So y plus 4 times 1 is just going to be y plus 4. X times both of these we have to distribute. That's going to be xy minus 3x. What I'm going to do is I'm going to subtract xy to get it on the left side of the equation, and I'm going to subtract 4 to get that on the right side of the equation. Now notice how there's a y in both of these terms. I want to factor that y out. And now what I can do, instead of multiplying by 1 minus x, I can divide both sides of the equation by 1 minus x. And we've got it. So now you see how we've got the y by itself. Instead of y, what we could do is we could write this as f inverse of x equals this quantity right here. Okay, so let's go to number 24. It says, is the inverse of this graph here a function? So what they're testing us on here is the horizontal line test, HLT. And what you do is you draw horizontal lines and you see, does it cross the graph at more than one point? Well, you can see here, this horizontal line is crossing at this point, this point, this point. So that means it fails the horizontal line test. It means that the inverse of this graph is not going to be a function. When you do the vertical line test, you're testing to see if the original graph passes that vertical line test. If the original graph is a function, the horizontal line test is testing if the inverse is a function. In this case, it fails since the horizontal line crosses more than once. Okay, for number 25, it says find the vertex of the quadratic function f of x equals negative 2x squared minus 8x plus 5. The important thing here is to remember this formula, negative b over 2a. And remember, this is a, b, and c. Negative b over 2a gives us the x-coordinate of the vertex. It also gives us the axis of symmetry of the parabola. So for this one, negative b is the opposite of b. That's going to be 8 over 2 times a, which is 2 times negative 2. This is negative 4, so we have 8 over negative 4, which equals negative 2. Now, negative 2, that's the x-coordinate of the vertex. If we put it back in, we can solve for f of x, which is the y-coordinate of the vertex. So let's go ahead and do that. We've got negative 2 squared, which is 4, times negative 2 is negative 8. Negative 2 times negative 8 is positive 16, plus 5. So we have 21. Well, actually, let's do it this way. This is 8 plus 5 is 13. So negative 2, 13 is your vertex. Okay, number 26, it says write this function, which is the same one we worked with in number 25, in vertex form by completing the square. Okay, so to refresh on completing the square, what we're going to do is we're going to think of f of x as y, okay, and what I'm going to do is I'm going to subtract the 5 to the other side of the equation, just to kind of get it out of the way. So we have y minus 5 equals negative 2 x squared minus 8x. I'm going to factor out this leading coefficient. Okay, so I divided both these by negative 2, factored it out, and now what we're going to do is we're going to complete the square. So the way you complete the square is you take half of b, so our b value is 4, so half of 4 is 2, and then what you want to do is you want to square it. So 2 squared is 4, but because it's in parentheses, this is actually negative 2 times 4, which is negative 8 that we added to the right side of the equation. We have to add negative 8 to the left side. So now we're getting y minus 13 equals negative 2, and if we factor what's inside the parentheses, we get x plus 2, the quantity squared. Now I'm going to add 13 back to this side to get the y by itself, and now that's our vertex form. So you can see the vertex is going to be at negative 2, positive 13, same thing we got here. The one that's grouped with the x has the opposite, the opposite effect on the graph. So this is in the form y equals a times x minus h squared plus k. hk is the vertex, a is the stretch, compress, or reflect. In this case, the negative 2 is reflecting it, the 2 is stretching it, it's opening downward. So you can see the vertex is negative 2, 13. The axis of symmetry goes right through the x-coordinate of the vertex, that's x equals negative 2. The y-intercept, what you want to do is you want to set x equal to 0. So the y-intercept is going to be 0, 5. But to find the x-intercept, what you want to do is you want to set the y value equal to 0, okay, and solve. So in this case, what I would do here is I'd probably use the vertex form one here, the one where we completed the square. So if y is equal to 0, I'm going to subtract 13. Okay, so that's negative 13. I'm going to divide by negative 2. That equals x plus 2 squared. So these negatives cancel, and I'm going to take the square root of both sides. Remember, when you do that, you get two answers. That's plus or minus square root of, we'll just say 13 halves equals x plus 2. And then I'm going to subtract 2, so this comes out to negative 2 plus or minus square root of 13 halves. And you can simplify that down further, but those are going to be where it crosses the x-axis, the x-intercepts. Okay, so for number 27, it says write the vertex form of the parabola with a vertex at negative 1, 3 and passes through the point 0, 6. Okay, so here you can see we're working with this vertex form of the parabola, this one right here. HK is the vertex, so we have y equals a times x minus a negative 1 squared plus k, okay, which is our y coordinate of our vertex. Now if we put 6 in for y, 0 in for x, these two negatives cancel and give us positive 1. So we get 1 squared is 1 times a is a. Subtract 3, you can see a is equal to 3. Now if we take the 3 and we put it back in for a, we've got our equation in vertex form. So it's going to be y equals what a equals, which is 3 times x plus 1 squared plus 3, and that's our vertex form. Okay, for number 28, they're giving us a function, f of x equals x cubed minus 2x squared minus 8x. And then it wants to know the end behavior, the real zeros, and it wants us to graph it. So we're working with, graphing polynomials. The first thing I would do is look at the end behavior, and what you want to do is you want to look at that leading coefficient. The leading coefficient is positive, which tells us that the graph is going up to the right. But because it's an odd degree, it means it's going to be going the opposite direction to the left. If the leading coefficient is negative, it's going to be going down to the right. And if it was an even degree, the two end behaviors are the same, either both down or both up. Okay, one way you can test this is if you put like a value in for x. So say for example, if x was 10, 10 cubed is 1,000. So when you're over here at 10, x is way up here at 1,000. So you can see it's going up. This term is growing faster than these two terms, so you can kind of ignore these. This is going to be the most influential term. If you put negative 10 in, a negative 10 cubed is negative 1,000, right? So that's going to be going, down to the left, right? So it's way down here. So you can test some values just in the highest powered term. But what we're going to do is we're going to write it in the limit notation. So we're going to say the limit as x approaches infinity, meaning as x goes to the right, f of x, which are the y values, are going to go to positive infinity, meaning going up. But if you say the limit as x goes to negative infinity, meaning as you go to the left, what happens to the y values? Well, f of x is going down to negative infinity. As far as finding the zeros, what you do is you set the y value to 0 to find the real zeros, and those are going to be our x-intercepts. So what we do is we just set y equal to 0, and let's factor out an x. That's our greatest common factor. Okay, and then let's see if we can factor this further. That's going to be x minus 4 and x plus 2. Okay, so we're just factoring. Now if we set each of these groups equal to 0, you can see that we're going to be getting 0. We're going to be getting positive 4, 1, 2, 3, 4. And we're going to be getting negative 2. So those are our zeros, 0, 4, and negative 2. And we already got our end behavior. You can see these zeros are just occurring once. There's no double zeros or triple zeros. So when we graph it, it's just going to go right through these points, something like this. Now this is just a rough sketch. It's got our x-intercepts, it's got the basic shape of the graph, it's got the end behavior. If you wanted to plot some additional points in between these x-intercepts, you could get a little bit better idea about how far down this graph goes or how high up it goes, etc. But that's a pretty good sketch. Okay, number 29, it says find a fifth degree polynomial with zeros at x equals 1, 2, and negative 3. So the important thing that they're testing us on here is they give us the zeros, but how do we find the polynomial? Well, x minus the zeros are the factors. So if x equals 1 is a 0, x minus 1 is a factor. If 2 is a 0, x minus 2 is a factor. If negative 3 is a 0, x minus negative 3 is a factor, but the two negatives cancel, so it becomes x plus 3. So if you set these groups equal to 0, these factors to 0, you're going to get these zeros right here, 1, 2, and negative 3. But notice if you were to multiply these together, it's only going to come out to x cubed. We really want this to be a 5th degree polynomial. So what I'm going to do is I'm going to make this one squared and that one squared. So there's more than one correct answer, but you can see now if you add these exponents, 2 plus 2 plus 1, that gives us a 5th degree polynomial with the zeros 1, 2, and negative 3. Now, 2 here is going to be what they call a double zero, or a 2 with multiplicity 2, meaning it occurs twice. Same thing with negative 3. Negative 3 is a double zero, or negative 3 has a multiplicity of 2, meaning it occurs twice. For number 30 now, it says divide 3x cubed minus 5x squared plus x plus 2 by x plus 3. What they're testing us on here is we can either do the polynomial long division, or because this is a linear factor, we can do the synthetic division. We're going to do negative 3 here, and we're going to use the coefficients of our polynomial, 3, negative 5, 1, and 2. Now, if it skips over from x cubed to x, for example, you'd want to put a placeholder of a 0 there. You want to make sure it goes in descending order, and if any terms are missing, again, put that 0 as a placeholder. When you divide by x plus 3, you want to use the opposite sign here, negative 3. If this was x minus 3, I would make this a positive 3. And then what you do is you drop down that first term, okay? Negative 3 times 3 is negative 9. Add those together, multiply on the diagonal, add straight down, multiply on the diagonal. Let's see, what does this come out to? Negative 129, and add straight down, negative 127. This last number is the remainder. We started with x cubed, it goes down by 1 degree. This is 3x squared minus 14x plus 43 plus a negative 127, okay, divided by x plus 3. So whatever the remainder is, it's over the divisor, what you're dividing by. Instead of plus and negative, I could just write this as minus. Okay, for number 31, it says use the remainder theorem to find f of 5 given that f of x equals this polynomial here. So the remainder theorem is very similar to the synthetic division. So what you would do is you put 5 over here and you put the coefficients of your polynomial, 4, negative 2. There's not an x squared term, so I'm going to put a placeholder 0, 2x, and 3. And then we just do our synthetic division. We bring down the 4, we multiply on the diagonal, we add straight down, we multiply on the diagonal, we add straight down, we multiply on the diagonal, we add straight down, we multiply on the diagonal. Let me go to the calculator on this one. I did this one a little bit earlier. It's 2,260. And if we add straight down, we get 2,263. And this last number here is the output. So basically, when you put 5 in to your function, you're going to get out 2,263. You could also do this direct substitution, put 5 in for x and simplify, but this is, the remainder theorem is like a little bit of a quicker way to find out what that output is using the same method we did when we did synthetic division. So the last number is our output, so f of 5 is 2,263. Okay, for 32, it says simplify and write in a plus bi form, 3 plus 2i divided by 4 minus I. Well, we don't want to have I in the denominator, just like how we don't want to have a square root in the denominator. So to get rid of this I in the denominator, what we're going to do is we're going to multiply by the complex conjugate. We change that sign in between these two terms. So if this was plus I, I'd make that minus I. Now all we have to do is just FOIL, okay, as if you were multiplying two binomials together. So if we do that, let's see what we get. 3 times 4 is 12. The outer gives us 3i, the inner gives us 8i, so that's going to be 11i. 2i times I gives us 2i squared. Okay, and then over here in the denominator we have first terms give us 16, outer 4i, inner negative 4i, those cancel, and the last two terms we get negative I squared. Now remember, I squared is equal to negative 1. This is very important. And remember, I represents the square root of negative 1. So when we see this I squared here, we can replace it with negative 1. So that's negative 1 times 2 is negative 2, plus 12 is 10. And here we have I squared is negative 1 times a negative is positive 1 plus 16 is 17. But we don't want to leave it in this form. We want to actually split this up into two parts. 10 over 17 plus 11 over 17i. That's what they call the a plus bi form. It's the real part plus the imaginary part. Okay, for number 33 now, it says list all possible rational zeros. Rational means ratio, right? It can be written as a fraction of an integer over an integer for f of x equals this polynomial. So the rational root theorem or rational zero theorem, however you learn it, whichever name, you take all the factors of the constant over all the factors of the leading coefficient. like this. You'd say all the numbers that go into 5, which would be plus or minus 1 or plus or minus 5, divided by all the factors that go into the leading coefficient here, which are plus or minus 1 or plus or minus 3. So now if we write these values down, it could be 1 over 1, which is a negative 1. It could be positive 1. Let's see, it could be, negative 5, positive 5. It could be 1/3, or it could be negative 1/3. All right, so I'm taking any numerator over any denominator. So did I get them all? 1 over 1, 1 over 3, okay, 5 over 1, and I forgot 5 over 3. So 5/3 and negative 5/3. And if you want, you can put them in order from lowest to highest. That's oftentimes helpful. But again, any numerator with any denominator. Okay, for number 34, it says find all the rational zeros of this function. So what we're going to do is we're going to use our rational root theorem, our rational zero theorem, to narrow down the possible rational roots. So we're going to take all the factors of 8 over all the factors of 1. So it'd be plus or minus the numbers that go into 8, like 1, 2, 4, and 8, over all the numbers that go into 1, which are just plus or minus 1. So this works out pretty easy. It could be 1 or negative 1, 2 or negative 2, 4, negative 4, 8, or negative 8. But what we're going to do is we're going to test them out using synthetic division. So let's just say if we wanted to see if 1 was a 0, we're going to take the coefficients of our polynomial and just do the synthetic division. So bring down 1, multiply on the diagonal, add straight down, multiply on the diagonal, add straight down, multiply on the diagonal, add straight down. Now notice how we got 0 remainder. That tells us that 1 is a 0, meaning that 1 is an x-intercept, okay? And x minus 1 is a factor. But when we do the synthetic division, remember this brings this polynomial down by 1 degree, and we could factor this further to x minus 4, x plus 2, and then 1, so this would be like x minus 1, since that was a 0. So we fully factored it, so our zeros would be 1, 4, and negative 2. That's where it's going to cross the x-axis. So you want to try to bring it down to a second degree quadratic, so that you can either do the quadratic formula or you can factor it to find the remaining zeros. Here we start off with a third degree, so we really couldn't factor this, so that's why we did a rational root theorem. So for 35, it says find a polynomial function with real coefficients, okay, that have 2i and negative 1 as zeros. Now the interesting thing is that notice how if we want to write a polynomial with real coefficients and we have an imaginary 0, like a complex 0, then what that tells us is that the complex conjugate will also be a 0. So if 2i is a 0, we also know that negative 2i is a 0. Or if we had like a plus bi is a 0, then we would know that a minus bi is a 0. They come as conjugate pairs if the coefficients of the polynomial are going to be real, like that. So here, let's go ahead and write this out. We know that x minus 2i is a factor, since 2i is a 0. We know x minus negative 2i is a factor, since negative 2i is a 0. And we know x minus negative 1 is a factor, since negative 1 is a 0. So it's always x minus the 0. So if we simplify this a little bit, this would become plus 2i, this would become plus 1. Let's FOIL this out. So first gives us x squared. The inside and outside cancel. Negative 2i times positive 2i is negative 4i squared, okay, which that comes out to negative 1 times negative 4 is positive 4, so we have x squared plus 4 times x plus 1. So here if we FOIL this, we get x to the third. Outer gives us x squared, inner gives us 4x, and the last terms give us 4. So this would be our polynomial function, f of x equals x cubed plus x squared plus 4x plus 4. So the key was really to recognize the complex conjugates concept if the coefficients are real. Okay, number 36, it says f of x equals x squared minus 4 all over x squared minus 2x minus 8. We want to basically graph this rational function, finding the domain, the asymptotes, the holes, the x-intercepts, the y-intercepts, etc. So the first thing I recommend doing is when you have a problem like this is see if you can factor it as much as you can. So the first thing I would do is factor the numerator, x plus 2, x minus 2, and I factor the denominator, which is x minus 4 and x plus 2. Now notice how that x plus 2's cancel numerator and denominator. So what that tells us when you have a factor in the top and the bottom that cancel out is that there's going to be a hole, oftentimes referred to as a removable discontinuity, at this value negative 2. So if you set x plus 2 equal to 0, you get negative 2. That's going to be the x-coordinate of the hole. And so what you can do now is take the negative 2 and put it back into your equation in place of x. So negative 2 minus 2 is negative 4. Negative 2 minus 4 is negative 6. And that reduces to 2/3. So that's the y coordinate of our hole. So let's go ahead and plot that on our graph. -2 2/3, that's right about there. Draw an open circle. Okay, the next thing I want to do is look at the asymptotes. So the asymptotes, first thing I would do is look at the denominator. You can see that the denominator can't be 0, that's undefined. So if we set x minus 4 equal to 0, we get x equals 4. That's our vertical asymptote, 1, 2, 3, 4, and we can draw that as a dashed or dotted line at 4. Now for the horizontal asymptote, what we do is we look at the highest degree term in the numerator and the highest degree term in the denominator. Notice it's a tie, they're both x squared. So we look at the ratio of the coefficients. So 1 over 1 gives us a horizontal asymptote at y equals 1. So that's going to look something like that. Now if the degree in the denominator was higher, like if this was x cubed and that was x squared, then it would be y equals 0 as our horizontal asymptote right at the x-axis. And if the numerator's power was higher, like if this was x cubed and this was x squared, then we would actually get a slant or diagonal asymptote, and we'd have to do the polynomial long division to find an equation of that slant asymptote. So now let's take a look at the domain. So the domain is whatever the x values can be. The main thing here is we don't want the denominator to be 0 because you can't divide by 0, that's undefined. So x cannot be a 4 and x cannot be -2. So sometimes you can draw this on the number line, that helps. So -2 or 4, we don't want those values, but it could be everything else. So if we want to write this in interval notation, we could say the domain is from -infinity to -2, not including -2, so we're using the parentheses, not the bracket, and then from -2 to +4, not including +4, union 4 to infinity. So that's going to be your domain. Now as far as the x-intercepts go, if we want to find the x-intercepts, what we really want to do is we want to set y equal to 0. The only way that y will be 0 is if the numerator of this fraction is equal to 0. So by setting the numerator to 0, x minus 2 is equal to 0, we get x equals 2. Our x-intercept is at 2, 0. So that's going to cross right there. The y-intercept, what we can do is we can set the x value equal to 0. So if we put 0 in for x, we get -4 over -8, which is +1/2. And so that's going to be our y-intercept right there. So now you can see that the graph is going along like this, and then it goes like that, approaches the asymptotes. And if we plot some additional points, like say for example x equals 5, we get 3 over 1, which is 3. So at 5 you're at 3 right here. So you can kind of see the graph is going to look something like that. So these are like the two branches of our rational function. So for number 37, it says solve the inequality. So here what you want to do is you want to get everything on one side of the inequality sign and set it to 0. Then what you want to do is you want to factor it as much as you can and set those factors equal to 0. So if we set them equal to 0, we get -3, okay, for this one. If we set this one to 0, we get x equals 4. But see how it's less than 0? It doesn't want to equal 0? That means that these are going to be open, meaning it doesn't include these values. Now what we're going to do is we're going to do something called sign analysis, and we're going to pick a test value in each one of these intervals, okay? So say we test, like for example, like -4. If I put -4 in here, I'm going to get a -8, which is negative. A -4 plus 3 is -1, which is negative. A negative times a negative is a positive, so I'm just going to put a plus sign here, but we really want a negative value. We want something that's less than 0. Okay, but now let's pick a number in this interval. Let's say, like for example, 0. If we put 0 in here, we get 0 minus 4, which is negative. 0 plus 3, which is +3. A negative times a positive is a negative. Now let's pick an point in this interval. Let's just say like 5. 5 minus 4 is 1, that's positive. 5 plus 3 is 8, that's positive. A positive times a positive is a positive. We want where the graph is less than 0, meaning where it's negative. So that's going to be from -3 to 4, not including -3, not including 4. So that would be the interval that would make this inequality true. Now, if we were to graph this in like 2 dimensions, what you would see is that this is actually a parabola, okay, x squared minus x minus 12. It's opening up like that. And so here you can see is where it's below the x-axis. Okay, over here is where it's above, meaning where it's positive or greater than 0. But we're just analyzing on the number line in 1 dimension. So for number 38, the last problem here, we want to solve this inequality, but what you want to do is you want to get a common denominator. You want to combine these into one fraction. So I'm going to multiply the numerator and denominator by x minus 1. So that's going to give us -3x plus 3. I'm just distributing the -3 this is x plus 2 all over our common denominator, x minus 1. So if we combine like terms, we get negative 2x, 2 plus 3 is 5, and we want this to be less than or equal to 0. So now what you're going to do with these rational inequalities is you're going to set the numerator's factors and the denominator's factors equal to 0. So if we do that, we get x minus 1 equals 0, that's going to be x equals 1. If we set the numerator's factor to 0, we're going to get, let's see, negative 5 divided by negative 2, that's going to be 5 halves. Okay, that's like 2.5. And we want it to be less than or equal to 0. The important thing to pay attention to, though, is the denominator can never equal 0, right? Because that would be undefined. So this is going to be open, meaning it can't include 1, can't be 1. But the numerator can equal 0, 5 halves. So this is going to be closed, meaning it includes that point. Now we're going to pick points in each of these intervals, starting with, let's say, maybe 0 is a good point here. So if we put in 0, a negative 2 times 0 is 0, plus 5 is 5, that's positive. 0 minus 1 is negative 1, that's negative. A positive divided by negative is a negative. Let's say we pick, for example, 2 is in this interval. A negative 2 times 2 is negative 4, plus 5 is 1, that's positive. 2 minus 1 is 1, that's positive. A positive divided by a positive is a positive. And let's just say we pick like 10, okay? So we do negative 20, plus 5 is negative 15, that's negative. And we said 10 minus 1 is 9, that's positive. We have a negative divided by a positive, which is negative. We want to know where it's less than or equal to 0, meaning where it's negative or 0. So this is going to be negative infinity to 1, not including 1, and from 5 halves to positive infinity. This includes 5 halves, so we want to use a bracket for that, whereas the other ones we're using parentheses because it doesn't include those points. So great job. I hope this helps you review for the first quarter pre-calculus exam. If you want to see quarter number 2, I'm going to be doing a video for that, and you can check that out right over there. Otherwise, if there were concepts here that you didn't understand or want more review on, I have all these concepts on my Mars Math Tutoring YouTube channel. I'll see you in the next video.